Hello, everyone. Welcome to Next Generation Science Standards 101. This is part 4 of a series of online modules. And in this module, we will be learning about engineering design in the Next Generation Science Standards. My name is Kirk Robbins. I am a consultant in the Puget Sound region in Washington State. And on the screen, you can see the URL to a blog that I run, and you also have my Twitter handle if you're interested in connecting on Twitter. Like the other modules in this series, it is intended for any K-12 teacher or administrator, anyone who wants to learn about engineering design in the next generation science standards. These modules were specifically designed for the districts on the screen, but we're hoping that lots of districts in Washington State and maybe even outside of Washington State will find these online modules to be useful. We want to acknowledge Washington State Laser, and more specifically the South Sound Laser Alliance, for providing funding for these online modules of professional development. We also want to thank the regional science coordinators in Washington State. There are several activities that were used in these modules that came from the regional science coordinators, as well as lots of other people around the state and around the country. For this session, you will want to have at least a partner, if not a small group, to work with. Please do engage with the tasks. In this module, there will be times when you will leave this site and watch some other video clips where you will hopefully engage in an engineering task that we're going to ask you to do. So please do engage in the tasks. You'll probably want to download the documents to your computer, maybe print some of them out. If your district is requesting you to, please use the Google form, which will be a way for you to submit some of your thinking and reflections. Set aside about 60 minutes, and for this session it might take a little bit longer than that, so it might take closer to 75 or even 90 minutes, depending on how much time you spend on the engineering challenge. And please be prepared to pause the video occasionally. All of the links and documents will be found just to the lower right of where you're watching this video. Here's our agenda for the module. We're going to start just by thinking about what do we mean by engineering and what are some of our own experiences as learners and teachers of engineering. Then we're going to switch gears a little bit and think about, well, what do we mean by technology and what might be our students' ideas about technology. Then we'll dig into engineering design in the next generation science standards. How is that similar to engineering processes that we've used in the past, and how might that be different? We're going to read a piece of text and look for different parts of engineering design in the text. And we will finish up by watching a video of some students doing some engineering, and we'll really be looking for strategies that the teacher is using. If you've been going through these modules in order, the last time we were together was a session on the cross-cutting concepts. We watched the video about how wolves change rivers. We looked at the video of the hand bubbler and used the hand bubbler to think about questions about the cross-cutting concepts that we might ask children, students. We did a little bit of reading from the appendices in the Next Generation Science Standards about the 7 cross-cutting concepts. And we finished by watching a video of some teachers doing some professional learning about the cross-cutting concepts. I wanted us to revisit the science and engineering practices. Module 2 was about the science and engineering practices, but really most of that learning that we did was more from the science side of the science and engineering practices. So you'll notice they're called the science and engineering practices. So engineering is right there in the practices. Each of those 8 practices, those are things that engineers do also, but they might look a little different than they look in engineering. So for example, when you look at practice 1, asking questions in science and defining problems in engineering, there's a little bit of a flaw there, right? Because engineers also ask questions. Practice number 2, developing and using models. Usually in science, we're building models that are predictive or that help us to construct an explanation. In engineering, when we build a model, we're usually using that model to test out an idea that we have, testing out a solution to a problem. Practice number 3, planning and carrying out investigations. In science, typically we're using that to find a cause and effect relationship. A lot of times in engineering, when we're planning and carrying out investigations, we're trying to learn something about some materials that we might use in our solution. So the practice is very similar in science and engineering, but there just might be a slightly different lens that we're using for those practices. So we have engineering in the practices, and engineering is also in the disciplinary core ideas. And in these modules, we haven't really talked too much about the disciplinary core ideas. In the past, we've referred to this as content. In the next generation science standards, all three dimensions are content. One of the big shifts in the next gen is that in the past, we've had kind of three domains in our disciplinary core ideas. We've thought of physical science, life science, and earth space science. Well, now we're adding this fourth domain, which is engineering, technology, and applications of science. So engineering is in the practices, and then there are also disciplinary core ideas about engineering that we want kids to understand. So cross-cutting concepts are third dimension in the next generation science standards. The engineering doesn't necessarily pop out as much when we're looking at the cross-cutting concepts, but these are also concepts that engineers use, and they might think of them a little differently than we do in science. So for example, in science, when we're looking at cross-cutting concept 2, cause and effect, a lot of times in science we notice an effect, a phenomena, and we're trying to figure out, well, what causes that? In engineering, that's flipped a little bit almost. We know the effect that we want. How do we design something to get that effect? So still thinking about cause and effect, but again, kind of like the practices, might have just a little bit of a different lens or way that we're thinking about those. So we've taken a look at this slide in each of the modules, and this is just really to reiterate this very important shift in the next generation science standards, which is this idea of three-dimensional learning. So when we're doing engineering, we also want to be engaged in three-dimensional learning. We want to make sure that we're engaging in practices, in disciplinary core ideas about engineering and science, and also using those cross-cutting concepts. So in the last couple of years, I've done several face-to-face professional development sessions on engineering, and one thing that comes up with lots of different grade levels of teachers is, well, why do I even need to know about engineering? I'm a science teacher, not an engineering teacher. I've heard things like that. So I just wanted to go through a few reasons why we do need to know some things about engineering and need to be teaching engineering. In that first bullet, engineering ideas actually didn't just arrive with the next generation science standards. They've been part of our Washington State science standards. We have our application ELER in our 2009 standards, and there was also engineering ideas in our standards before that. So it's not a new idea. Engineering is already being assessed on the 5th grade science MSP, the 8th grade science MSP, and on the biology end of course in high school. So those are some reasons we need to know about engineering. It's a huge part of the next generation science standards. And in the framework for K-12 science education, the document that I've referred to as the cookbook before, just really makes some strong statements about the importance of engineering. And one of the things that I've had several teachers talk with me about is that a lot of times when you start to do engineering in your classroom, kids who've maybe been marginalized or haven't seen as much success in science, a lot of times when there's an engineering task, that's when they really shine. So there's just something about engineering that really opens up our instruction to all of the kids. Another great thing about engineering is that it's really a place where we can teach kids to be good collaborators, a place where they can focus on their speaking and listening skills, and just focus on those 21st century skills about being a skilled worker and thinker and working on grit and all those types of things. So I'd like us to pause just for a couple minutes, and if you haven't had a chance to download one of the versions of the notebook, if you could please do that now. And on page 2, I want you to think about the following questions. What is your background as a learner of engineering? And you might want to open that up not only to in-school experiences, but outside of school experiences that you've had as a learner. What are some experiences you've had as a teacher of engineering? And then what do you think are some important terms or concepts that we should be teaching kids about engineering? So take a couple minutes just to jot down a few bullet points and then talk a little bit with your partner about what you wrote down. So you've had a chance to talk, hopefully, with a partner a little bit about your initial ideas about engineering and your experiences, learning engineering yourself and teaching some engineering things. What's really interesting in working face-to-face in professional development sessions, a lot of times we might not feel like we've had a lot of official engineering learning experiences ourselves. So that one of the hopes of this module is that by the end of doing this module, you'll feel like you have a better understanding of what engineering is about, and that you'll feel more confident in being able to start to lead your students in some learning about engineering. So with that, what I want you to think about with your partner, with your small group is, so engineering, what might be a student-friendly definition of engineering? So just take a couple minutes and brainstorm what might be a student-friendly definition for engineering. So what I'd like to have you do next is there's a really nice short video clip that's down in the links section. It should say video, what is engineering? And it's a short video that was created in Australia. So just be ready for a couple of references that might be a little off for us as Americans, and be ready for an Australian accent. So I want you to pay attention in the video. What is their student-friendly definition for engineering? So you've had a chance to watch the video, which is a pretty cool video, and obviously you have the link to that if you want to use that with any of your students. And the punchline of the video is really that engineering is about solving problems. Hopefully that makes it seem a little less scary. There's almost a part of me that wishes that we hadn't called it engineering in the next generation science standards, because I think it conjures up certain images. It makes us think more of a career than just this idea of solving problems. So hold on to that really when we're talking about engineering, we're talking about how do we help kids become better problem solvers. Because to be honest, we have a lot of very interesting problems as human beings right now, and we need some people who are going to be good at solving them. So we have our simplified definition of engineering, that engineering is about solving problems. One thing that I want us to do next is to think a little bit about technology. So we have our acronym STEM, right? Science, technology, engineering, and math. That's pretty popular these days. So what do we mean by the T in STEM? What is technology? So on page 3 in your handbook, you have a formative assessment probe called Is It Technology? And I want you to just take about 4 minutes to answer that by yourself. And again, we don't have a definition for technology that I've given you, and that's on purpose. I want you to just access your own definition for technology. And then after you've taken a few minutes to answer this by yourself, I want you to work with your partner and talk about, okay, what rule were we using? And also think about how might your students engage with a probe like this or some type of similar activity that would get them to think about what is technology and what might not be technology. So you've taken a few minutes, hopefully, to answer the Is It Technology probe and to do some sharing with a partner. We're not going to go through all of the answers to that right now, which I'm sure will be a little frustrating for some people, but that's okay. In a couple slides, we're actually going to look at a definition from the Next Generation Science Standards for Technology. But before we do that, I want us to think about something. This is some research that was done a few years ago by the folks who put together Engineering is Elementary, which are some instructional materials to help elementary students learn about engineering. And this is very similar to the probe that I had you answer, and the way that this works, this is kind of a crazy looking chart here, but basically we have items that the kids were asked about that were electrical items, and you can see that the blue is the pre-test kids did well. They understood that a keyboard and that a cell phone and a laptop, that those things were technology. They also mostly understood that something like a bird or an oak tree is not technology, that those are natural types of items. You can see where the confusion tended to come in were items that were non-electrical technologies, so things like a broom or a bicycle. You can see several kids before instruction didn't tend to think of those as being technology. Afterwards, the red is the post-test, you can see that after some instruction and understanding about technology, most students were selecting those types of items as technology. So that's really the big misconception. I feel like I see some of that thinking even in school systems where we talk about, well, we want to do STEM, so do we need to have Chromebooks and iPads and all those types of things, which are great. But there are also these non-electrical technologies that we might need. We might need some duct tape and cardboard and hot glue guns and things like that, so that we can have kids actually designing technology, not just using educational technology. So let's look at some definitions from the Next Generation Science Standards. On page 5 in your packet, you actually have a piece of text that has a lot more than just what's on this slide, but I wanted to draw our attention to these two definitions. So for engineering, in the Next Generation Science Standards, it talks about engineering as any engagement in a systematic practice of design to achieve solutions to particular human problems. So just like in the video, we're solving problems. And in this definition, we kind of add a little more to that. We're adding human problems, okay? For the definition of technology, we have all types of human-made systems and processes. So any human-made system or process, that would be a type of technology. And then this goes on to talk about not in the limited sense often used in schools that equates technology with modern computational and communication devices. So similar to what we were talking about on the last slide, we're not just talking about tablets and phones and laptops. We're talking about pencils and pens and clothing and all types of systems, right? Technologies result when engineers apply their understanding of the natural world and of human behavior to design ways to satisfy human needs and wants. So I would pause the video and take a couple minutes just to skim over some of the definitions that are on page 5 in your handbook. So we've talked a little bit about a definition for engineering. We've talked a little bit about what we might mean by technology. The next thing I want you to think about with your partner are what might be the steps that engineers use to solve a problem, right? So we kind of have an idea of ways that scientists, right, might figure things out. How do engineers solve problems? I want you to just brainstorm with your partner. What do you think some of the things are that engineers do? So the 4 images here, I just did a quick Google image search for engineering process and found these plus lots of other ones. One problem in engineering education has been that there hasn't just been one engineering process that's kind of been the consensus model for how engineers do their work. So that's been a little bit of an issue in engineering education. Most likely when you and your partner were brainstorming, you probably had some of these ideas that you came up with. People tend to talk about, well, you need to figure out what is the problem. You might need to do some research, figure out what other people have tried, do some brainstorming, probably pick an idea and make some kind of a plan and then test out that plan. There's something about engineering that's pretty intuitive to us. We have a sense of how it is that engineers solve problems because as adults, we're solving problems all the time. So I think we're using that type of process a lot. In our 2009 Washington State Science Standards, in our application ELER, we had something called the technological design process. And it wasn't a circular process. We usually thought about it as a linear process. So we had defining the problem, gathering information, which is kind of like doing research, exploring ideas, which might be like brainstorming. Then we'd pick one of those ideas or combine some ideas and make a plan. Then we test that plan out, and then we communicate the results. So that's what a lot of us have been teaching in our classrooms, and those are the ideas that are being assessed on our current assessment system as of the spring of 2015 when I'm recording this. So what is the new engineering design process? What might that look like? So engineering design in the next generation science standards looks like this. There are three components. We have defining the problem at the top there, developing solutions, and optimizing solutions. So in some ways it's very simple, but there's a lot that's happening in this process, right? One thing that's an innovation, something new, notice that it's not just a cycle, but that the arrows go back and forth, right? So you can be bouncing around in here. In Module 2, when we were talking about the science and engineering practices, we kind of talked about the messiness of that there are several entry points to the practices and that you're not just following them step by step. Same thing here, right? We have these three components, but there's some bouncing around that happens. And the orange text boxes, I called out some important terms. So a couple terms that live in the defining the problem part of engineering design are criteria and constraints. So we're going to do some more thinking about that in the rest of the module, but really criteria are goals. What are we trying to do with the problem that we're solving? And then constraints are really our limits. That might be things like we only have so much time, we have certain materials, we have a budget, so constraints. And then some ideas that might live in optimizing and in developing solutions are failure points. So how do we help kids to identify failure points? One thing that we notice when we first get kids engineering is that certain kids might just, if something doesn't work immediately, they might just throw their hands up and say, oh, I'm not good at this, I can't do it. So how do we help them to notice specifically what didn't work? And then what can you do to fix that? So failure points. Another idea that we'll talk about in this session is trade-offs. And really what trade-offs are about is sometimes we can't have all of our criteria. Even though we want all of those goals met, we might have to trade some off. And we'll talk about that a little more as we move forward. In your notebook, there are 4 pages that are about engineering design. And what I did is engineering design, some of the standards in the next generation science standards about engineering are banded. So you'll see here on the screen, if you are a teacher of kindergarten through 2nd grade, you're going to want to look at page 6. If you're a 3rd through 5th grade teacher, you're going to want to look at page 7, middle school teachers, page 8, and high school teachers, page 9. And what you're going to want to look at are how is that graphic maybe a little different at your grade band? What are the engineering standards that are listed there? Okay. Just take some time to do that reading, circle some terms or ideas that might be new to you or to your students, and then jot down some questions that you have about that short reading. Let's talk a little bit about the reading that you did on engineering design. So one thing hopefully that you noticed is that with all of the grade bands, we're focusing on those 3 components. So every grade level is doing something to learn about defining problems. Every grade level will be doing something to learn about developing solutions. And every grade level will in some way be digging into optimizing solutions. And there is a progression for those. Each of those pages represents all of the engineering standards for that grade band. So hopefully that is a useful document just to see for your grade band, these are the engineering ideas that we should be teaching to kids. And what I'm going to talk about now is going to be maybe a little confusing, but there are kind of 2 different flavors of engineering standards. There are standards like the one that I just popped up in this text box that are ETS standards. So this one, it says 3-5-ETS1. That means this is a 3 through 5 grade band standard, and it's on defining problems. Okay, and you'll notice that this is all just about the engineering part. Okay, now there are other engineering standards that I call integrated standards. So here is 4-PS3-4, and that means this is a fourth grade, excuse me, physical science performance expectation. And it says apply scientific ideas to design, test, and refine a device, so that's the engineering part, right, that converts energy from one form to another. So you can see that this orange text box, that standard is a little different than the one that's in purple in terms of the orange one has some science ideas that we're using. The standard in the purple box, we could use any science idea with that. We haven't been limited with what science idea we might use in that. So you might want to return to those pages that you were looking at before and just do a little thinking about how those two sets of standards, the ETS standards versus the others, are similar and different. So in order for us to think a little bit about these three parts of engineering design, defining the problem, developing solutions, and optimizing solutions, on page 10, there's a very short blog post. This is the story of some high school students who designed a new type of ketchup cap to solve a problem. So I want you to just quickly read over that article and just put a 1 or a 2 or a 3 to mark where are the students defining the problem. You'd put a 1. Where are they developing solutions? 2. Where are they optimizing solutions? And jot down a 3. So let's do a little bit of thinking about the reading. So these aren't intended to be the right answers. These are just some things that I've had participants talk about in face-to-face professional development sessions. So places in the text where the high school students might be defining the problem. It talks about that the teacher launched this with, "It really bugs me when blank," right? So that's a really nice instructional strategy for helping kids to identify their own problem. There's a spot in the text where it says some initial surveys indicated that others shared their distaste for the problem. So they're trying to make this case that this actually is really a problem, right? Another part in the text that might fit into this component was they pored over patents to verify that a solution didn't already exist. So one of the things that I really like about this article is that these two students spent a lot of time actually defining the problem, and they even had to convince their teacher that this was a problem. So they had to engage in some argument just to get their teacher to allow them to do this ketchup cap design. Places where they might have been developing solutions, in the text it talked about they each sketched out 30 different ideas for a design. That sounds like developing solutions to me. From 60 potential designs, they narrowed it down to 5. So I think that's probably still in that developing solutions, right? And then places where they might have been optimizing a solution, there was just a part in the text where it said they focused most of their energy on perfecting their design and not so much worrying about patents and the money part of this. So I'm sure there were lots of other places in the text that you could have matched with these three different components, but I just wanted you to have a real case of some students doing some engineering and then connect that to our three parts of engineering design. So I wanted to take a couple minutes to share a story about engineering that's an authentic human problem. It's the story of a boy named Liam, and Liam lives in South Africa, and he was born without any digits on one of his hands because of something called amniotic band syndrome, which prevents the developing digits from growing correctly. But the story really starts with a gentleman named Richard Van Az, and Richard is a carpenter in South Africa. And one day Richard loses control of one of his saws and mangles most of his right hand. So Richard isn't a rich guy, and he realizes that a prosthetic hand is going to cost a lot of money, so he tries to figure out how to design a prosthetic hand himself, and he starts to run into some barriers, and he gets online, and he finds a gentleman named Ivan Owen who lives in Bellingham, Washington, in the United States. And Ivan specializes in these large puppet hands for the theater. So they begin doing some online collaboration via Skype and sending some things through the mail. And at some point, they just feel like they need to do some work face to face. So Richard's family, they combine some frequent flyer miles together and they fly Ivan out to South Africa for a couple of weeks. And here's the part of the story where I'm not super clear on, but somehow Liam, the boy I told you about at the beginning, Liam's mom hears about Richard and Ivan and the work that they're doing and says, hey, I have a son, Liam. He doesn't have any fingers on his right hand. Could you help design something for him? And these gentlemen say, sure, of course we can do that. So they put together a hand for Liam. And what's really interesting, there's a great story here about criterion constraints, right, in our next gen engineering design process in our first area about defining the problem. So Liam actually had some criteria himself. A lot of times a client, right, Liam is the client in this case, will have some criteria, and one of Liam's criteria was he wanted it to look like a robot, which is actually a good thing because they probably were not going to be able to make it look like a real human hand. So you can see here's a picture of the robo hand, and the way that this works is that because Liam does have a wrist, when he moves his wrist, that's what causes the fingers to open and close. I'd highly recommend, there is a video link off to the side. Take a minute just to watch that. It's a video of Liam using his new hand. And this engineering story continues because these gentlemen contacted MakerBot. They were interested in turning their design into something that they could 3D print. So they did a couple iterations of their design, and now anyone with access to a 3D printer and the internet can print out a prosthetic hand for about $5. So if you remember when we looked at our definitions for engineering and technology, it talked about authentic human problems, right? So this is just a great story of some people who aren't trained engineers. These are just people who like to fix things and like to solve problems, who are solving authentic human problems for lots of people. So that's what we want our students to be good at. We want our students to be good at solving real, authentic human problems. So what we're going to do next is we're going to do our own engineering design challenge, and this might be a little tricky because we're not face to face and I can't just reach through the computer screen and hand you some materials. So we'll have to kind of play along as best we can. So first thing that we want to do with students is to launch the problem, right? In this case, I'm going to do a lot of the defining the problem for us. So the way that I want to pitch this is that we actually work for a company called Comfort Swings, and we specialize in swinging benches like what you can see here in the picture. Okay, and most of our swings have really been limited to this type of design, and then one day we have a client who has a very specific request. We have an elderly woman who's lived in the same house for her whole life, and she remembers back to when she had this tire swing on this giant oak tree, and she knows that her tire swing days are probably over, that that's not safe. So she wants our company to help design a swing that would be a bench swing that would hang on this angled branch in her old oak tree. So our team at Comfort Swings built a model of this, and you can see the model in the picture here, right? So we have our tree with an angled branch, and we have this bench type of swing. So with your elbow partner, I want you to just make a claim. What do you think is going to happen when I'm going to show you a video of testing that swing right there? So what do you think might happen when we pull this swing back and release it? So you've shared some predictions about how you think this model might behave. In a second, I'm going to have you download the video of me testing this model, and I want you to really think, what do you notice about the motion of the swing when we test it, and what do you think might be causing that motion? So download the video that says swing design and watch that with your partner and think about these two questions. What do we notice? What might be causing that? So when you watch the video, you probably noticed that there was this really kind of crazy motion of the swing. It was just all moving around in a very not safe way. We would not want our elderly customer to be on a swing that had that type of motion, right? Our learning targets for the swing challenge are as follows. I can collaborate with a group to define a problem. So you'll be working with your partner, a small group, to define a problem. You're going to collaborate with a group to develop solutions to a problem. So you want to see if you can come up with maybe 2 different ideas of how to solve this. And then I can collaborate with a group to test and optimize a solution to a problem. So we're going to try in this very short amount of time to engage just a little bit in all 3 components of engineering design. Spend a little time defining the problem, developing solutions, and then trying to optimize one of those solutions. So we're going to do some defining the problem together. So we had talked earlier about there are really 2 things when we're defining the problem that we want to attend to. One is, what are the criteria? So the criteria we've talked about so far for our work here at Comfort Swings is it needs to be a bench type of swing. It's not a tire swing, okay? It needs to hang on the natural angled branch. So in other words, the solution can't be just to cut off the branch and make something that hangs straight out from the tree. We want to maintain that natural angled branch. And the swing needs to swing safely and smoothly, right? We don't want it to be wobbling around like that model swing that we looked at. So those would be our criteria. And one thing we mentioned a little bit was the idea of a trade-off. So one thing to think about is we might have to make some trade-offs with our criteria here, okay? So then the other aspect in defining the problem are, so what are our constraints? If we were doing a face-to-face session, I would have very specific materials for us to use. I can't just give you materials because this isn't a face-to-face session, but I would really like you, I would ask that you spend a little bit of time designing something. So you may, if you have any craft sticks or dowels or pencils or blocks, some type of tape is probably going to be necessary, some string, paper clips, some washers or coins. Those would be the type of materials you want. And really the first thing you want to do is to set up some model of an angled branch, right? So just like in the model that I had, you want to have some type of a pencil or a stick that you have at an angle, and then set up a swing as best you can, like the model that I showed you, and then test that out to see if it kind of has that wobble like the model swing in the video, and then see if you can figure out something that wouldn't have that wobble when it swings. Okay? In a face-to-face session, we probably also have some time constraints, and I'm sure that you have some time constraints as you're watching this. So take some time to gather up some materials. So here are some recommendations for some steps you might want to use. Whatever materials you've pulled together, the first thing you might want to do is to create that angled branch, and then to create a swing, a bench type of swing. And then you really want to start to think about, okay, what could we do to this model so that the swing would not wobble that way, like we noticed in the video that I played. And then once you have something that seems to be working a little bit, try to optimize that. How could you make it even better so that it meets the criteria that we talked about in the last slide? Hopefully you've had a chance to spend a few minutes with a partner or small group designing some type of a bench swing that would work on an angled branch and not wobble like the one that we saw in the video. So I'd like you to take a couple minutes with a partner or your small group to think about each of the areas or each of the components of engineering design in the next generation science standards. So in the defining the problem area, spend some time thinking, where in the challenge were you defining the problem? And did you ever have to, what I'm calling bounce back? So like in the diagram, where there are those two-way arrows, did you ever have to go back up to the defining the problem circle and spend some time there? Developing solutions. Where in the challenge were you developing solutions? What did that look like? What were you doing when you were doing that? And then optimizing solutions. Where in the challenge were you optimizing solutions? What failure points did you notice? What were you thinking and how did you navigate some of those failure points? Did you have to make any trade-offs? Were there some criteria where it was kind of hard to stick to that? I know in some face-to-face sessions I've done, some of the trade-offs are that, well, we didn't have to cut off the branch, but we made kind of support that maybe doesn't make the branch look quite as pretty as our client may have wanted, but it definitely makes a sturdier swing. So spend just a little bit of time debriefing your challenge and connect it to the 3 areas of engineering design in the next generation science standards. For our last activity in this module, I want us to get into the classroom and look at, so what does it look like when we have kids who are engaged in engineering? So this is a video that's part of the Teaching Channel's series of videos, and we're going to spend about 10 minutes or so watching a group of 5th and 6th grade students, and they've been doing some work on roller coasters. They're designing some different roller coasters. On page 11, you have a sheet where you can take some notes. The main thing that I really want you to look for, what strategies is the teacher using, and something that might be helpful for you is, because probably most people watching this video are not 5th or 6th grade teachers, and even if you are, to think about how might I modify these strategies for my grade level or for my classroom. So as you're watching, don't get too caught up in the specifics. We're really harvesting strategies. What are the strategies that this teacher uses that we as teachers might use for any type of engineering challenge? So now that you've had a chance to watch the video and take some notes, please work with your small group or with your partner and share what strategies did you notice, and then what might be some ways that you would modify those for your classroom. I just wanted to share a few things about some of the strategies that are in the video. So on the screen, you'll see some of those strategies. So for example, there was chiming, was one of the first strategies that the teacher used. And that's really kind of a structured student talk move. So it's a way of structuring talk so that the kids can share some of their ideas, and the teacher really steps aside to let the kids see themselves as resources for each other, and that their ideas and the things that they've learned are important. Another strategy that she talks about is sketching, which I think most of us use sketching, but the way that the teacher in the video uses it is really intentional. So she had the kids do individual sketches that needed to be labeled, and then they would use that sketch to kind of sell their sketch. I think her wording was to sell your sketch as the first design of the day. So then when they got into their small groups, they needed to come up with a group sketch so that they knew what it was they were going to be designing. Another strategy was that the teacher used a simulation. So that's not something we're always going to use, but sometimes we might have some online free simulations that kids can use. Some important things to notice about how the teacher used that was that she really had the kids look at failure points. She didn't use that language, but that's what she was doing. She had them write down on sticky notes, if it didn't work, their roller coaster simulation, what was the failure, why do you think that happened, and what could you do to fix it? Those 3 questions are so important as teachers of engineering to help point to kids. Well, what didn't work? Why do you think that didn't work? And what could you do to fix it or make it better next time? The teacher also uses a real intentional use of materials. So she talked about how she tries to use minimal materials at first. She adds more things over time. And then the use of a budget is very interesting, right? That creates some more constraints and really makes the kids think about trade-offs. Very intentional use of roles. So for this challenge, she had an accountant, a recorder, an organizer, and a measurer. She might use some different roles depending on the challenge. And then this isn't a real explicit strategy that she talked about a lot, but if you notice, she's just such a good listener and so good at questioning, right? She's questioning kids at all stages of the design process, and not in an aggressive or intimidating way, but she's just really wanting to know, why did you pick that? Why do you think a hill would make it go faster or slower? All those types of things give her great formative information.
We are almost to the end of our session on engineering design in the next generation science standards, so let's go over some take-home messages to summarize. So the first take-home message is that engineering is about solving problems. If you remember that very first video clip that we wanted, engineering is about solving problems, and that's really important. As I mentioned earlier, I think that when we think of engineering, it conjures up a certain type of image, and it really makes us think about a career. And engineering in the next gen isn't about turning every student into an engineer. It's about helping them to be good problem solvers, because that's going to be really important regardless of what career they go into. Technology is more than just electronic devices. We want kids developing all kinds of technology. Engineering should be taught in every grade level, K through 12. I'm not sure if that really popped out in what we were talking about in the session, so I just wanted to reiterate that. We want kids to be doing having some engineering experience in every grade level, not just certain grade levels. Engineering design has three components that we learned about. We define problems, we develop solutions to those problems, and then we optimize solutions. So be thinking about those three components and how we can start to engage students in doing those three things. One really fabulous thing about engineering is it not only helps kids to become good problem solvers, but it's a way to engage them in being collaborative. It engages them in working on speaking and listening, which is in the Common Core ELA standards. It helps them to develop some grit to where they're going to stick with things and try to figure some things out. And it really helps them to work on some of those 21st century skills. So then that leaves us with a question, which is, so where might we intentionally start to add some engineering opportunities to our current units of study? A lot of times, there are already some engineering activities in the instructional materials that we might have. Maybe we just weren't thinking of them as engineering before. A lot of times, I know in middle school and elementary instructional materials, towards the end of a unit, there will be an opportunity for kids to take what they have learned and then apply that. And more times than not, that is an engineering type of component that might just require a little bit of tweaking on our part to turn it into an opportunity for kids to define a problem, develop some solutions, and optimize solutions.
We are winding down to our final reflection here on this session. So if you want to turn to page 12 in your packet and answer those three questions, if your district or building has asked you to, please click on the Google form link and complete the reflection that is in that form. So what's next? We're at a space here where this is our last of 4 modules. It's highly possible that we might have some more modules coming out in the future. Whether we title that Next Generation Science Standards 102 or 201, or we just add a few more modules to this set, I'm not sure. But hopefully you have found these to be useful, and we look forward to putting some more online professional development like this together for you soon. Thank you so much.